Hi, my name is Eric Koch. I'm a postdoctoral researcher at the Harvard and Smithsonian Center for Astrophysics. It's my pleasure to present to you some of the first work on nearby galaxies in JWST's first 2 years. I'm presenting this on behalf of a much larger collaboration of about 130 people that make up the Physics at High Angular Resolution in Nearby Galaxies Survey, or PHANGS. And so we were lucky enough to have some of the first pictures of nearby galaxies that JWST ever took. And this is one of them, perhaps the one that's become the most famous so far from our survey. This is the galaxy NGC 628. It's almost completely face on from our point of view from here within the Milky Way. And what we can see is this beautiful grand design spiral and the immense amount of structure that JWST identifies by tracing the emission of this galaxy in the mid and near infrared. Now we're going to come back to this galaxy in a few places, but just note that this complex structure isn't just found in this one galaxy. We actually have a larger set of 19. And this is what we were observing in the first year with JWST. And just to give you a quick sense of just the amount of structure and diversity amongst these galaxies, we're just going to zoom in to a handful of them. What you see in the blue light is the near infrared. It's mostly telling us where the stars are located. And the orange is telling us about the emission from dust that's mixed together with interstellar gas. And what you can see within these different galaxies is the different structures that they have. Some have spiral arms, some have these sort of nuclear rings around their centers, and some have these bars that trace gas flowing into the center. There's so much structure within these galaxies. And this really begs the question, what are we actually looking at? And in particular, what I'm going to be talking about here is the vast range of bubble-like structures, so the absence of the gas, and what we're tracing is sort of the shells using JWST. And so what are these from, and what can we learn from them? So let's go back to this picture of NGC 628. So to understand how such bubbles form, and why we're seeing so many of them, we need to actually zoom in into a single star-forming region. And so from here, this view of the entire galaxy, we're going to zoom down into much smaller scale, sort of 100 light years or so. And now we're transitioning so that this full screen would be about 100 light years, the same size as that circle in the previous slide. And what I'm going to show here is a numerical simulation of an individual star-forming region, what we call as a cloud. Now this is sped up by quite a bit. We're essentially watching the evolution of this cloud as it forms stars over several million years. And what we started out with is this collection of cold gas. The motions in the gas are quick enough that we get supersonic shocks everywhere. And as a result, it forms these filamentary-like structures that you can see here as we zoom around. Within these filaments, some of the regions can then gravitationally collapse, allowing gravity to take over in small portions. And this is ultimately what leads to the formation of stars. Now, if this process was so simple and just included turbulence and gravity, the story wouldn't be nearly as exciting as it is in reality. What we need to account for is the fact that once those stars turn on, they inject a significant amount of energy back into their surrounding areas. And they do this by different mechanisms. One of the first that turns on are these protostellar jets that you can see starting to appear here in the simulation. So even though these are coming from just a single star or stellar system, they affect a massive area surrounding them, influencing the ongoing star formation in the rest of the cloud. After a while, stellar winds start to contribute. That's leading to some of the bubble-like structures that you're seeing here towards the top of the screen. All while turbulence is continuing to create these filaments and gravity is continuing to form stars. And what we're watching here is the assembly of a larger stellar cluster resulting from this cloud as a whole. Over time, significantly larger cavities begin to be formed around this cluster. And this is the birth of these much larger holes in bubbles that we saw previously in the galaxy NGC 628. Now, one of the most important parts is this is actually how we think star formation turns off. Over the lifetime of one of these clouds, only about 1% of the gas is turned into stars. The rest is held up. It's not able to gravitationally collapse. And we think that it's mostly the energy from these stars after they form that shuts off or stops the remaining gas from forming stars. And it does this by heating the gas and starting to blow these bubbles and dispersing the cloud as a whole. So since this cluster has been around for a while, we're now starting to see these larger cavities that you could imagine starting to be identified in these other nearby galaxies. But there's one more trick up our sleeve, and that's in these massive stars. The brightest ones that give off the most amount of energy, despite having the most fuel, they burn through it very quickly. And as a result, their lifetimes are short, and so they die in supernovae, and that's the shock that you saw go through the gas, while they're still in the cloud that they formed from. So all of this detail is happening within just a single region of these nearby galaxies. So one of the most interesting things about studying these galaxies is we can build up massive samples and look at how the evolution of these bubbles and star formation exist. And one of the other interesting points is, in particular, new work about our own solar neighborhood around the sun. And so I'm going to take this box and I'm going to put it now on top of a bird's eye view that we get if we zoomed out above the Milky Way from our position at the sun. This is a diagram showing a combination of data and models. It's what the gas would look like in our surrounding neighborhood as traced in 3 dimensions. And this is brand new work that's been enabled by the Gaia satellite, which gives us distances and proper motions of the nearest stars. So this blue region here is a model for what we think our own local bubble is, and the sun just happens to be passing through, and right now we're close to the middle. So now I'm going to switch from a top-down view to an artist's rendition of what this bubble looks like from the side. Now the sun is that thing in the middle. It is not to scale. The sun's much smaller and not nearly that bright. And the things that you see around the edge are all of the nearest star-forming regions to the sun. And in work led a couple years ago by my colleague, Catherine Zucker, she showed that we can actually trace the history of this bubble as it began from a set of supernovae and expanded over the last 14 million years. And as it expanded, it drew up gas and dust, leading to the formation of all of the nearest star-forming regions to us around the sun. And this is enabled again by this Gaia satellite, where we can trace back in time where young stars were when they initially formed. This is potentially very interesting because it suggests that not only does stellar feedback turn off star formation in individual clouds, but can also seed the location of the next generation of stars. Now, unfortunately, we can only get this kind of detail within our own solar neighborhood. So while we have a very good idea of this process from our own local bubble, it's hard to generalize to a larger sample with the data we currently have in hand. So let's zoom out again and see how this more broadly fits into our view that we get now with JWST and these nearby galaxies. So now that we've pointed out the bubbles, you're probably seeing hundreds of these. And just to give you an idea of why JWST is so revolutionary in this area, I want to take a step back and look at the data in combination with what we had access to before. This is the same image of the galaxy. We're just looking at a single filter, so it's shown in grayscale instead. This is the center of NGC 628, and I'm going to bring up in comparison the same wavelength as traced by the last generation of infrared telescopes, the Spitzer Space Telescope. And it becomes immediately obvious the limitations that we currently or that we previously had using only the Spitzer data. JWST's resolution and sensitivity is so high that we can now pinpoint these individual bubbles in a way that we just simply could not with previous data. And the location of these bubbles was really just one of the first surprises that we had as we started to get these pictures. So this particular image of NGC 628 was one of the first galaxies that, or nearby galaxies, that JWST observed. And initially, I was sharing these initial results at a conference with other researchers studying the interstellar medium and star formation. And it actually took people quite a while to believe that this was a real image and not a simulation. We're used to seeing these kinds of structures in this sort of infinite detail within numerical simulations of galaxies, but this is really our first time of seeing that structure in reality in a nearby galaxy. So we have all of these bubbles. We want to look at their properties and understand them as a whole, as a population, and better understand how they both stop star formation within individual regions, but could also potentially seed it around the edges of these bubbles as they grow. And so the initial work on this was led by my colleague Elizabeth Watkins as part of the rest of the PHANGS team. And she identified nearly 1,800 bubbles within this one galaxy. Now, this is the same image that I was showing before. It's now just reoriented along the celestial coordinates. That's why it looks like it's been placed at a different angle. So this would be sort of positioning it as you would see it on the sky. And from this large sample of bubbles, in particular, we found that these larger ones have these series of nested bubbles along their edges. And qualitatively, that's a similar picture to what we're seeing within our view from the local bubble. That newer star formation is triggered at the edges and it starts to form its own set of bubbles. And we're just seeing these nested sets of bubbles and holes at different stages of their evolutionary path. Now, this was a colossal undertaking to just identify these first set, but of course, we don't just have one galaxy, we actually have 19 with all of their diverse structures. And even over the past year, we've been expanding this sample with another program that's going to add, or is about to add, another 70 more. So we have almost 90 galaxies. If we're finding roughly 2,000 or so bubbles in each of these galaxies, this means that we're expecting that the data that we're already have in hand or are about to have could allow us to identify well over 100,000 of these feedback-driven bubbles. And such a large sample is critical because, again, we're looking at a several mega-year process, several million years, and we only get this one snapshot. So we need a huge sample to understand how these bubbles vary and are connected to previous generations of star formation by just looking at a massive sample. We need to build up sufficient population statistics to better understand their age and evolution. And the way that we're going to be doing this is via a citizen science project called BubbleZoo. This is in collaboration, again, with PHANGS, but in particular with Liz Watkins and Eric Rosalowski and myself. This will be a new project appearing soon on the Zooniverse platform. And I'm showing you just an example of what one of our small cutouts will look like, where you can help us explore these very intricate data sets and identify all of these bubbles. This is essential for us to better understand how this is connected to star formation and eventually how galaxies evolve through many different cycles or many different evolutionary cycles of this star formation process. This sample will be well over 1,000 times larger than anything that we've had before. And so it's really critical to be able to measure their properties so that we can learn a number of unanswered questions about this star formation process. And so with that, I'm just going to leave you with my conclusions and thank you for your time. Again, this is about work on behalf of the PHANGS collaboration, in particular, the early work done by Liz Watkins, who is also attending this workshop. And if you're interested in her work, you should absolutely go and ask her more questions about it. I can be reached via email, or you can find more information about my research on my website. And I'd like to thank my colleagues at the CFA, Catherine Sucker and Theo O'Neill, who helped provide some of the slides for this presentation. So in summary, JWST is showing us that nearby galaxies are ubiquitously filled with these bubbles. Those bubbles can be similar to what we are in within our own solar neighborhood in the current location of the sun. And we'll be launching this BubbleZoo project to help us identify the largest sample of these bubbles that have ever been traced before and use that to better understand the star formation process. Thank you.